So these are the, if we draw this information in a tabular form, we again see that cubic it is possible in PBF, primitive, body centered and face centered, and A is equal to B is equal to C, alpha is equal to beta is equal to gamma is equal to 90 degree, and for its example are sodium chloride, zinc blende and copper. These are the three examples of cubic primitive unit cell. Tetragonal, it is possible in primitive and body centered. A is equal to B is not equal to C, and alpha is equal to beta is equal to gamma is equal to 90 degree, and its examples are white tin, TiO2 tin oxide, SnO2 and calcium sulfate. These are the some of the examples. And orthorhombic, this is possible in primitive, body centered, face centered and end centered in all the unit cells. In all the crystal lattices it is possible. A is not equal to B is not equal to C, alpha is equal to beta is equal to gamma is equal to 90 degree. And second example are rhombic sulfur, rhombic sulfur and KNO3. I will request you all that please see the video till the end, because at the end of the video we will solve some of the numerical problems which are very interesting and they are very important for the examination point of view. Now comes hexagonal. It is possible only primitive, and length of edges A is equal to B is not equal to C, and alpha is equal to beta is equal to 90 degree, but gamma is equal to 120 degree. Its examples are graphite, ZNO, zinc oxide and CDS. These are example. Now rhombohedral, this is also possible only in primitive unit lattice cell, primitive lattice, and A is equal to B is equal to C, alpha is equal to beta is equal to gamma, but they are not equal to 90 degree. All are different from 90 degree. Its examples being calcite, CaCO3 of course, HGS, mercury sulfide, this is also called as cinnabar. And in monoclinic, this is possible in primitive and end centered, and A is not equal to B, all are different, and alpha is equal to beta is equal to 90 degree, but alpha is equal to gamma, gamma is equal to 90 degree, but beta is not equal to 90 degree. And monoclinic sulfur, its examples, and Na2SO4, sodium sulfate, (10H2O). These are all given your NCERT book, so you can see that also. But if for learning purpose, I am including it in my video. Triclinic, this is possible only in primitive, and all the three edges are different in length, and alpha is not equal to beta is not equal to gamma, and that is not equal to. No two angles are equal, and they are also not equal to 90 degrees. And its examples being K2Cr2O7, Cu copper sulfate, potassium chromate, copper sulfate, and H2BO3. So this is the table. You can learn it. And now we come on to our next topic, that is number of atoms in a unit cell. See, crystal lattice is made up of very large number of unit cells, and each unit cell has constituent particles. They may be atoms, molecules, or ions, and these constituent particles are located in a unit cell at different positions. So first we will consider primitive cubic unit cell. We have learnt that this is a unit cell in which at corners the constituent particles are present at corners. So in a cubic structure there are 8 corners. So see, if we consider this, there are 8 corners in a cubic structure. 1, 2, 3, 4, 5, 6, 7, 8. 8 corners are there. So there are 8 constituent particles. But these constituent particles, they are the part of adjacent unit cells. Adjacent unit cells. So each constituent particle is also a part of adjacent unit cells. And how many adjacent unit cells each particle shares? There are 8 adjacent unit cells which are shared by each particle. Now see, if we consider this particle, this is shared by 4 of the adjacent unit cells at this side and 4 adjacent unit cells at this side, left and right. So there are 8 adjacent unit cells. So each unit cell share 1/8 of each constituent particles, and if there are 8 constituent particles, then 1/8 into 8, and 1 unit constituent particle is shared by 1 unit cell in a primitive cubic unit cell. Now I hope that this is clear. This concept should be clear so that numericals and all the theory is based on this. So because each small constituent particles represent only the center of the particle occupying in open structure, and these are shared by all the 8 adjacent unit cells. So one unit cell share only 1/8 of a constituent particle, and if there are 8 constituent particles, then the part one constituent particle is shared by 1 unit cell. Now if we see body centered cubic cell, in body centered what we have learned, that the constituent particles are present at the corners, and beside this there is 1 constituent particles at the center of the body. Then one constituent particle, 1 atom here, plus 1 at the center. then in unit cell there will be two constituent particles or atoms, molecules, whatever. So in body centered cubic there are two constituent particles, because the particle which is present at the center of the body is not shared by any other unit cell. So it is only shared by the unit cell in which that is the particle is present. See here they are corner constituent particles which are shared 1 by 8, and therefore they are 8 constituent particles, hence they are total one constituent particle is there, and in center one particle is there, and that is shared by exclusively by that unit cell. So the total constituent particles are 2. Now we come to face centered cubic cell. How many particles are there in a unit cell of face centered? See, in face centered what we have learned, that there are 6 faces. There are 6 faces in a unit cell. If we take a simple diagram, there are 6 faces in a cubical structure. So there are 6 particles. See, face centered cubic cell. Each face has one constituent particles, each face. But this particle is shared by one more adjacent unit cell, and this face centered particle is shared by 2 unit cells. So 6 face centered will be shared by 2, and 1 unit cell will share 3 atoms, 3 particles. And these 3 particles, beside this, at the corners there is 1 constituent particle. So 3 plus 1 is equal to 4. 4 atoms or 4 constituent particles per unit cell. So what we have learnt, that if it is primitive cubic unit cell, the number of constituent particles is only 1. Constituent particle atom per unit cell is 1. And if it is body centered, then the number of constituent particles are 2. And if it is face centered cubic cell, then number of constituent atoms, constituent particles are 4. Because at the face each constituent particle is shared by one more adjacent unit cell. So now I hope now this is clear, because this theory will be utilized in our numerical problems. Now one more thing in theory part, that what are close-packed structures. Close-packed structure, this is also very important. I again request you to please continue with the video till the end of the video point, so that the most important part of the lecture is not missed. Now close-packed structures. What is close-packed structure? In solids, what happens? The constituent particles are closely packed, leaving the minimum vacant space. Vacant space should be minimum. So our drawing the structure should have the principle that the vacant space should be minimum. Now we consider close packing of particles in one dimension. How can we draw? Suppose these are the particles. So this is in one dimension. They are touching each other at a point. So this is the arrangement by which these particles can occupy the minimum space, and minimum vacant space is left. Now, if we see what is the coordination number in this arrangement, we see that each particle is joined by two other particles. This is 1 and 2. So coordination number, we say that it is 2. Now we come to, this is the first. Second is close packing in two dimension. Again, here it is, first we draw a structure in one dimension. Now, how can we draw the second row? In second row, we can draw, one way is, this is the way. Means one over the other. One over other, and leaving the gap. This is the vacant space. These are the vacant space. Triangular vacant spaces. This is the one way of drawing, of putting the other rows. And the other, this is the first method. Other is, if we are having one dimension, and the other is drawn like this. Here one over another, in this one, first case, one over another was placed, and here the other layer is placed with one particle at the empty space of the first row. This is the second method. Here each particle is in contact with 4 particles. So here coordination number is 4. But here what happens? In this case, second case, what happens? I think this first layer is not visualized because the color is, see, this was the first row. So in this case, there are, if this is the particle, there are 6 surrounding particles which are in contact with a center particle. So we say that here coordination number is 6. So which is more efficient? This second method is more efficient. Why? Because the empty space in this is less and coordination number is more. Coordination number is the number of constituent particles that are in contact with the central constituent particle, central atom. Now, this is called two-dimensional hexagonal packing. Hexagonal close packing. And this is called two-dimensional square close packing. And as if we call it this A, this row, this is B, then again this row will be of A type. These first and third row will be the same at the same places. So A, B, A. This is called A, B, A, B type. A, B, A, B type. Because every